Welcome to a keynote that is between you and the social hour.
No pressure.
It's no pressure, 45 minutes most. The social hour will be in the terrace room where all the other social activities have been so far. So after Kathy is through, migrate over there and get one, something like that. Right, Manu? Yeah, sounds right. All right. With that said, it is an absolute pleasure, it's an honor to introduce Kathy. Kathy Fiedler. I have known her for 20-something years. She joined our group as a postdoc in 96, somewhere around there,
One of those years.
And she came from a very unusual research background. People look at hardware and, somebody built it, it's logic, right? It's all logic, right? So logicians think it's logic, and it's algebraic logic, whatever, but there are actually people involved designing these things. And these people use diagrams. They don't use logical formulas with all quantifiers standing on their head and sigmas and pi's, whatever you see. And so she looked at how people actually understand these logics, right? And so there's two ways of thinking about it. It's human factors and logic, or logic and human use. And that was a really cool topic, and she got more into it, and she did different areas of that kind. How do people actually use what you guys do? Maybe not in software initially, but things like that. But in the last few years, Kathy has migrated to what do people do with the fancy stuff that you put out there? And it's finally time to have somebody here who tell you what they do. Kathy, it's your show.
Okay. Thanks, Matthias. And thanks to Jan and Manu and the organizers for inviting me to do this, and thank all of you for holding out till the last session of the day. I know everybody's tired. We'll try to keep it all awake and moving. So the title of Defensive Little Code is playing off the idea of big code and big data. This isn't news to anybody, right? We're seeing papers that are talking about how to take large volumes of code and do interesting things with it with machine learning and related techniques. And some of this is enabled by repositories that give us access to a lot of code. Now, when we think about exploiting existing code bases like this, we're not actually looking for a pile of bits. We're actually looking for the structure. What are the structures that are in the systems we're writing that we might want to explain to somebody else? And those structures can take a lot of forms. It can be the namings we use, how we distribute features. There's a whole number of different techniques that people are starting to look at through big code. This is a sample of topics out of a survey paper that came out recently, just talking about the space in general. Now, these same kinds of issues are starting to hit computing education, which is where I'm now doing a lot of my work. So we see people looking at improving syntax errors by exploiting code repositories, or looking at variation in student solutions so you can see what's going on in your class. Other ways to give feedback through big data means. And a lot of this work comes out of a really good place, which is help us support learning at scale, right? It's an issue. Many of us are feeling that issue quite intently. So there's quite a bit of motivation to figure out how to leverage tools to help us scale education and learning. But one of the things we have to be careful about is a lot of what's going on in big code, where we're looking for error messages and optimizations and things like that, is about tuning a product. But when we're in the standpoint of education, we're trying to tune a human, okay? And in some sense, what this talk is going to look at are ways in which we have to pay attention to the differences between how we tune products and how we turn humans in the context of education. There's a nice quote that opens Michael Jackson's Principles of Program Design from 1975, which says the beginning of wisdom for a programmer is to recognize the difference between getting the program to work and getting it right. And I thought this was an apt quote for this, because a lot of times if you use a big code tool blindly, you might be getting your code better. You might be getting it to work, but you might not be getting it right. And again, in education, we are trying to help them, while we still have their attention, work on getting it right. Okay? So big data can help us tell that a program is wrong. If we have enough data over time, we might be able to tell when it started to go wrong. But the big question for education is why. Okay? Now, as Matthias alluded to, I've gotten to this point of doing computing education coming out of the kinds of things that get talked about in this community. My dissertation work was looking at diagrams to reason about hardware, which was a fun project. I worked in feature-oriented software verification, analyzing access control policies, and I keep hitting this button the wrong direction. There we go. And recently, I've moved into computing education. And as Matthias suggested, it's part of this continuum that I've always been interested in, this interplay between formal models on the one hand and human reasoning on the other, and looking at how people reason within and about formal systems. So that's one of the perspectives I bring here. I'm really excited by a lot of the tools that I see coming out and the way they're helping us understand formal systems, but I want to make sure we're doing it in a way that's consistent with how learners are going to be using them. So this is going to be a story in kind of 3 parts. The first 2 are going to be case studies from things we've been doing in our research group. They're going to be talking about a project that tried to go from using big code and ended up needing little code. A project that started with little code and now is moving to big code / big data. There's some of a blurry line between those. And then frame it all a little bit. What do we see happening in an education context? Okay. All right, so let's start with the first one. I'm going to start with a problem called rainfall. Okay? And rainfall is a problem that we often use in computing education to see how students are doing at learning programming. So here's the problem statement. Write a program that takes a list or an array of numbers and produces the average of the non-negative numbers that show up before some sentinel value, like a -999. Now, I want you to take a moment. Think about roughly how you would write this code. I don't care what language you use your favorite, but just get a code structure in your head and just hold that for a slide, okay? I'll give you a moment. All right. Why might anybody care about this problem? I mean, this looks really easy. Well, because students historically do quite poorly on it. Okay, and that's kind of what's surprising. What could be hard about computing computing the average of a sequence of numbers? Why have students done badly on it? Well, if you unpack this problem, what you see is that there's actually 6 different tasks going on in here. You have to truncate at that sentinel so you don't take too much data. Ignore the negatives. If you're going to do the average, then you have to sum and count the data. And you need to make sure you're not going to do division by 0 in the process of doing average. And where this problem can get difficult for students is in weaving together the code for all these tasks. Right? So seeing how to do them in isolation is more or less okay. Weaving it together is a little more difficult. Okay? So that's kind of the perspective we're going to think about here. All right, so let's think about how you might solve this problem and how you might solve this problem. So one common solution that people come up with to this problem is some kind of single loop over the data. So whether you're doing this with a recursive program or an iterative program, you're going to do one pass over the data and keep a running count and a running sum. As you go, you deal with the negatives in the sentinel, and then you chop it off the sentinel and compute the average. Use clapping. How many of you came up with this style solution? Just okay. Now, some of you, I'm guessing, came up with something rather different, yes? Yes? Okay. It's always somebody. Okay. Another way you might go about this is to actually clean out the data first. Okay? So maybe you dealt with the sentinel, you got all the negatives out, so now you only have the data you want to actually average, and then separately you count it, sum it, and average it. Now, how many folks were in a solution more like that? Clapping. All right, pretty even. How many of you did something completely different? Come on, be proud of it. Okay. Students also land somewhere in the middle of this too. But in general, what you find is the single loop is the typical solution you'll get from somebody who's learning imperatively. And something like cleaning first is much more common for students who are working in a functional language. Now, why might that happen? Well, part of it has to do with the built-ins that students are often taught in functional programming. So if you look at this problem and say, oh, I'm going to use the length function as a way of part of my average. Well, the only way you can use length is if you first clean out the data. Okay. And students who are working functionally might often also use things like filter or a take while from Haskell, something like that. So a lot of it comes down to what libraries do they think to use ends up affecting their code solution. Okay? All right, so now what I did with this problem was really my big entry into thinking about computing education, because I went to visit somebody who was well established in the field, and he said, you know, we've been giving this rainfall problem for 30 years. How come students can't do this problem yet? And he knew about the work that we had done with how to design programs, which is a design curriculum that Matthias started and I have worked on. And the question was, would they do any better or do differently if we gave them something that had a structured design process under it? HDP also happened to have functional programming under it. So there's kind of two variables there. So we went off and did a study. We got data from students in 5 different classes that were all using the same curriculum and same general techniques. And if you mapped out the results, so on the left graph, you have the historical performance of students. So historically, in the data, and this is the data going back to the mid-'80s when this problem started, you have 70% of the students are doing some form of a single loop. The rest of them are getting nowhere. I mean, you can't even tell an organization to the code they have underneath. Whereas the data I had from the students coming out of functional programming and how to design programs, they had much more variety, and their most dominant solution was this cleaning it first. Okay? The other thing that was interesting is our error rate was much, much lower. Most of our students got started and got somewhere. So this result generated a fair bit of excitement because it was, first of all, the first time that anybody had looked at multiple ways of doing this problem, multiple options students had, and something different happened. Okay? So this kind of started me in a career in computing education. Now, understanding this graph and unpacking it leads you to ask a few questions. We really wanted to understand at that point, was this really about the programming language? Okay, I mean, we know the programming language wars exist. We weren't trying to stake a claim in it, but we wanted to see how much was this an issue. And if you're going to do that, you really have to get beyond this little rainfall problem about computing averages. Okay? So the next suite of work that we did, we gathered data on 6 different problems that had somewhat similar features. Some of them featured cleaning. Some of them featured chopping off at a sentinel. Some of them were things like palindrome that just had various traversals going on in them. And we gathered data from students working in different languages to see what we would see. And we started getting this data in, and the first thing we thought is, man, we want a tool to do this. We were sitting there by hand, like marking up these solutions and saying, these are the structures. This is clean first, this is clean whatever. We had about 6 of these structures that we were looking at. And we knew at this point, now this is 2015, that big data kinds of techniques are coming out. Surely tools can take this pain away from us. No. We tried, but none of the classification would work. And this, again, based on the tools at the time, we talked to a couple of people who had leading edge tools at that point. They didn't really make much progress with our data set. And I think part of it was there are just too many variations and nuances. Depending on what language, what libraries, students could have structured the solution in the same way, but syntactically the code would look very different. Okay? Now, hopefully the state of the art has progressed a little bit and we do better today, but at the time that wasn't enough. But there was a bigger problem. We had no idea why. Right? It could be as simple as, this was the last thing I covered in class, I'm going to get graded on this, so I'd better darn well use the features that my professor put in the last homework, right? It's amazing how many times you say students, how do you do this problem? And they say something. Say, did you say that because we just taught that yesterday? Uh-huh. Right? So we were pretty sure that that was part of it, but we really wanted to dig into why. And even if we had our magic classification tool, it wouldn't have told us that. So we shifted. And we decided instead that we had to go narrower and start doing this qualitatively, not trying to do it somehow quantitatively. So we had students come into the lab and talk aloud while working on programming problems. We gave them rainfall as one problem. We would give them a second problem that was a little more complicated. And we expected those two problems to trip them up at different places. And we just wanted to see what would they do, what design techniques, what approaches, what's pulling them towards what they're thinking about. This is what we are now going to code the transcripts for. Right? So we take these interviews, we have somebody transcribe all the transcripts, and we're sitting there now marking them up with pencil and paper. It's painstaking work, but you learn a lot from this. One of the things that jumped out pretty quickly is that the students were retrieving from memory things they already knew and trying to adapt them. Okay? In some sense, this is not surprising. This has been well known from cognitive science when they've done studies about how people program. You tend to grab something you know and adapt it. One of the differences between novices and experts is experts grab things that are more general. Novices grab very syntactically driven pieces of code. So just because they would know how to solve this, say, in Java, they wouldn't necessarily know how to solve it in another programming language. Okay, that's what happens at the novice level. So it was nice to get this insight and to know that it was backed up by other work. But this gets you to the question of, what do students think are similar problems? Right? We might think that doing this problem either with recursion and two accumulator variables would be the same as doing it iterative with two variables that you update. Many of us would say, yeah, that's the same solution. The students, it was not the kind of thing they necessarily picked up on as being similar. So when you think about similarity, again, we've got all these tasks. And they have to figure out similar things that are going to latch onto these tasks. So, for example, we'd see students not understanding what the sentinel did. And so they either just ignored that part of the problem or just threw a -999 somewhere in their code hoping it would work. But it was clear talking to them, they didn't know what it was there for. Right? So that was one thing that we saw. We saw they often didn't see the alignment between the tasks and the code. Right, so they might know that the plus statement they wrote down is helping with summing, but they didn't necessarily get that you needed the whole loop infrastructure to get your sum to finish properly, for example. Sometimes you'd find they'd say things like, well, I've never seen a problem that has to traverse data twice, once to sum and one to count. We've only ever done one of those. And true, that's subtle. That's a non-trivial jump. But here's the one that really got me. Some of them didn't know it was okay to have two variables or two parameters. How many of us would take that for granted? Me too. I was sitting there, what? They know they can make one variable and they don't realize they can put a second variable or a second parameter. This was a huge leap for the students. I don't think there's any way we would have detected that problem if we hadn't been talking aloud and watching what they were doing and trying to get them to describe their code to us. So the first takeaway from this is that the details and the abstractions that we take for granted, many of us as people who teach intro courses and see students like this all the time, they're not obvious for students. And this is the kind of thing that it's not clear to me that the big data style tools and the big code tools would help us pull out. So we really needed this little code approach to get to this insight. Now, this is an ongoing project for us. What we're currently doing, I have my PhD students finishing up on this. We are now running talk aloud experiments with pairs of problems, but different pairs. So we might give them one accumulating traversal versus two. So kind of like rainfall and something that just has to go down the list once. We'll give them problems with and without a sentinel. Or we'll give them a problem that parsing the input slightly makes it easier to do. And one time we'll give them the problem where it's parsed and one time where it's not parsed and see how their strategies differ. The third one is going out in the field in the next couple of weeks. So we want to see where the students are starting to struggle so we can try to understand more things like the two variable concern. And we want to understand what makes their solution structures diverge. Because in each pair of problems you could use the core of the easier one as part of the harder one. But they often structure their code very differently, which means they're latching on to something we hadn't expected. And this is the kind of stuff that we we want to understand. At this point, we have nearly a dozen of these problems that we use to understand student code structure. If anybody's interested in running experiments like this in your own classes, let me know. We're happy to share the problems with you. It's been a lot of fun. Okay, now let's go the other way. Now let's look at a project where we started with little code and ended up in big data. So for this one, you spend a lot of time when you're doing CS Ed often looking at students in intro classes. I think that's a bit of a myopia that we've had in computing education, is not often getting out of the first year. I was teaching an upper level, which for us was third or fourth year undergraduate course in programming languages, and I was really curious how well students knew some of the basic programming languages constructs. How well did they understand scope? How well did they understand aliasing? Should I depend on these coming into my class? And after all, these were students who'd been programming now for several years. They had internships, and of course they thought they were experts in Java. They would tell you that they were experts in Java. And so we brought them in for the course and decided to run an experiment where I'm going to give them a quiz. We do this at the beginning of the semester. I gave them questions on scope and aliasing expressed in Racket and in Java. Why Racket? Because Racket was the language we were using in the course, and they had all had it as freshmen. Okay, so it wasn't an out of left field. It was saying, what had you understood and remembered from 2 years ago, which we weren't expecting them to remember much, but it was a good baseline. And then what happened in Java, which almost all of them had had subsequently and done internships in. Right? So we expected them to have much more expertise in Java, just given where their trajectories had taken them. Now, the questions aren't going to be exactly identical, but they're going to get at the issue in each language. So, for example, the Racket program, one of them was looking at static versus dynamic scoping. So this is a kind of straight-up question that checks whether you understand scoping. So you bind x to value 3. You then create a function that closes over the value of x. Now you bind x to 5, and when you run the function, which value of x do you get? Okay, so it's a pretty straightforward test to detect whether you have static or dynamic scope. To look at static versus dynamic scope in Java, we created a question where we had a static variable a, which we bind on the outside. Inside a function, we create another a and assign it, and we look to see which value of a gets used in a main program. Okay? Said it's not an exact match of the Racket program. We didn't want to give them unnatural programs. Right? We wanted to give them things that they might encounter. Okay, so we give them about 8 questions, I think, where there's some in Racket, some in Java. And so now let's pull up the results. So I'm going to show you first, just on the pretest at the start of the course, what was their performance in each of the 2 languages. So the blue lines are what they did in Racket. This is percentage of students in the class getting this right. There's 66 students in the course. And the green line is correct in Java. And for the most part, with the exception of scope, they're pretty even on the other questions, right? So aliasing and parameter mutation, which are things that other studies in computing education have shown students really struggle with, they're not doing quite so well at that, despite them all being Java experts, right? Go figure. Okay. So now, what happens when we bring in the post-test, right? So the post-test, they're getting the same questions. I think we might have changed the numbers on a couple of them, but they were structurally the same bits of code. So in the interim, they have written an interpreter for each of scope and aliasing. They have written interpreters for parameter mutation. They have written test suites to test our language implementations for these features, and they've done quizzes on these features. So we should have gotten somewhere. Right? Well, they got somewhere in Racket. They didn't get quite so far in Java. Okay? All right, well, the course was using Racket. Should I be surprised? Yeah, I was surprised, because expecting that this could be a problem, after every one of these topics, we had half a lecture on what happens with this concept in Java. Okay, so we tried to teach them this, and it somehow doesn't register. Okay, so this should have been primed. What's the lesson for all of us here? Transfer of knowledge between either different subjects or between programming languages is really hard. There's a lot of educational research on transfer. When you want transfer to work, you have to have explicit instruction in the second context. Now, I did some explicit work in the second context, but I didn't have them go home and write programs in Java on these. I lectured about it on the board. It would have been interesting to have them actually do the assignments in Java and see if we would have done any better. I just haven't taught the class since then. Okay? So this was, again, it's an example of something that people who are not in computing education sometimes underestimate. That transfer is really a problem. Now, but we were interested in understanding this better. So now, one of my collaborators on this, Sriram Krishnamurthy, he was teaching programming languages. So in Sriram's class, instead of giving them the two languages, we give them versions of the Java questions, but now we ask them to write a justification for what they were thinking when they gave the answers. And again, we had this grand hope that what we were going to do was take their answers, run them through some great natural language processing kind of tool, and get a sense of what kinds of mistakes and misconceptions might they have about this topic. What do we need to address with education? So this example program, it's a simple checking for pass by reference example. So we create a new object of some class it was an office with like occupants and room numbers. We pass it into a function that assigns the parameter to another object with slightly different contents and just see which one printed out at the end. Okay, so it's straight up, do they think the changes to the object by reference are going to leak out? All right, here's samples of the answers we get in the free response, right? And we're doing the free response because we know from our previous work that getting students to talk about it is where we get insight. Okay, so F1 creates a new office object that replaces the other one's old value. It's not very precise, right? What replace means, for example, the office was set in the method but not returned. Okay, not quite sure what, they have a model that returning might have something to do with this. Even though F1 uses an office as an argument, nothing about it changes. Kind of missing the whole justification point in the middle, right? It goes on, okay? And the point of looking at these, we must have spent a month trying to classify these, trying to make sense of students who checked the same box on the multiple choice question as to what they would do, and looking at their answers and saying, are they thinking the same way? We couldn't tell what they were thinking, okay? So when you think about trying to do things like this with big data or machine learning kind of approaches to augment it, the problem is it's really hard to classify these free-form responses automatically because they lack detail and there's very inconsistent use of vocabulary. We had some students use the word reference to mean one thing and some students use the reference to presumably mean something else. How are you going to have an automated tool make sense of how people are using the word reference when they don't mean the same thing by it? Right? So this was a good example of something that we really didn't have any chance of doing a lot of automatically because the data was never going to be precise enough. At the same time, we really don't want to sit there and keep grading all this stuff by hand to figure out what students are doing wrong. So some of the work we have going on now is changing what we try to get students to give us as input into the process of what they're thinking to see if maybe we can get somewhere with some more automated techniques. So what we're doing now is if instead of us giving students questions and having them answer them and explain, we instead ask the students to generate things that they think are interesting multiple choice questions with answers. So if a student thinks that, aliasing, they're not sure what it would do, they got tripped up on this, they write down a little multiple choice question. And then we take these questions and we feed them out to the other students. And there's part of the protocol, there's a tool we've built for this called Quizius. And what the students do is they'll tag other answers and say, this one is similar to mine, when they give their justifications or their rationale. So basically what we're doing is what the students think are going on for similar solutions here. Now we can bring in machine learning to look at classifiers based on both the answers they're selecting and the things they think are similar. So the hope is that we can use this machine learning technique to get reasonable classifiers of the mental conceptions, the mental models that students have of these constructs, because then we might be able to tell, okay, you need help on this topic, you need help on that topic. If you come from a computing education background or any kind of science education background, this contrasts to a fairly heavyweight process currently exists called concept inventories. Some people have heard of the forced concept inventory, which is a standard test in physics that's given in first semester physics. You look to see how students are doing on these questions, and they've been very carefully designed to tell you, based on these mistakes, this is what you have wrong. And there's a lot of interest in generating some of these things for computer science. They take years, because you have to interview students about every possible answer and make sure they're measuring what you think they do. It's tedious work, and it often doesn't work for multiple courses, because your students have different background than students in other courses. So we're trying to see if we can use some of the machine learning techniques to bring that back again. So what's the takeaway? Using a little code, we can tap into these ill-formed and poorly expressed conceptions. It gives us ideas for extra problems to add into the mix here, but we really need to leverage those insights to create automated tools, right? So you need the little code to start, but you're never going to get anywhere with this unless you figure out how to do things a little more automatically. Now wait a minute. We're just trying to fix how students are understanding things. Surely we can throw a tool at it, like a drill tool, right? Everybody talks about computer-assisted instruction and drill. So you got a student who's writing some code. The code has a bug. And that bug clearly came from some bugs are just dumb typos, right? But think about it's a conceptual bug. It came from something the student didn't understand right. So can't we throw some kind of big code debugging system at it, tell the student, this is your error, and then maybe we can do other drill techniques to help them remove the consideration, the misconception that got them stuck. So the big code debugger will get the bug out of the code. It fixes the product. What we don't know is whether it fixes the human, right? Or tunes the human, right? I mean, we're not trying to like make them all robotics. But we are trying to fix the misconceptions that are here. So why can't we do this? Well, the problem is misconceptions are mental constructs. How do you figure out which misconception they had that led to that bug? Certain bugs could have multiple justifications. And so this kind of technique only works if you can reliably figure out what they're stuck on. And correcting misconceptions is subtle. Okay, this is another topic. I didn't remotely appreciate this when I started doing work in computing education. So here's a brief crash course in how misconceptions work, and you'll want to go to the reception and have something to drink after this, especially if you teach. So you got some concept stuck in your brain, right? And that concept is incorrect. It leads you to make a bug in your code. Let's say we figure out what the problem is. Now we're going to drill. Okay? However much drill you decide you need, there's studies on that kind of stuff. We drill, and you've built up now a new conception. But look at the picture. Those dots are not in the same place in your brain. Okay? What we would love to believe is that doing the drill replaces the blue dot with the green dot. That's not how it works. What actually happens is now you have both conceptions in your head. And the whole question is, which one do you retrieve more often? Okay? Misconceptions do not get erased. They kind of get papered over because you retrieve something else more often. So to increase your chances of retrieving things, you have to drill in context. We retrieve problems based on context. Remember what I said at the beginning? Novices, they'll grab things syntactically or with very limited scope of what they're thinking about. If you want them to grab from the green dot, you have to have trained the green dot on the context you want them to retrieve it in. And you've got to get that green connection to be stronger than that blue connection. So you hide the old misconception. Okay? So kind of the punchline here is these are things that most of us who have not studied education theory, we don't understand these things. That's no fault of ours. I mean, it's not the field we came out of. But if you're going to build tools to enhance education, you have to understand how learning works. Otherwise, you're not going to build something that has a viable model for actually making headway. It's kind of like the following. And I've heard this from speakers who come by and whatnot. I'm going to create this great, powerful tool to teach coding using machine learning. We're going to monitor the students' progress. We'll make code-specific suggestions. Their code's going to get better. The feedback will improve their skills, and this is how we're going to solve the CS learning problem. Woohoo, woohoo, I'll get a job, I'll get tenure, and life will be wonderful. Now, let's take the same sentence structure and instead pretend that you're working on cancer treatments. Okay? I'm going to treat cancer with machine learning. We'll monitor the patients, we'll make treatment suggestions, they'll get better, the doctors will get better, we'll scale medicine to the people who lack health care. The doctors can't wait to have this. We wouldn't dream of creating tools for cancer without talking to medical experts. Right? I mean, there's malpractice and like laws and all that stuff, but even just ethics. You wouldn't do this, but we do it for education all the time. We create tools that we claim are going to help education because we think it should help education. And the real problem is teaching doesn't mean that you understand how education works. Right? We know something about teaching, but it doesn't mean we've understood the cognition of all these mechanisms. Okay? And so that's just kind of the thing to take away, the caution that if you're going to go do work using big code, big data, whatever technique will be new in 5 years, if you're going to use that, talk to people who understand how learning actually works so that you can try to make your goals. All right, so little code, big data, CS education. What's happening here? We got two storm fronts plowing in at the same time, right? We've known about the machine learning storm front. I mean, that's clearly a thing. And computing education has become a thing. We see it a lot in the US, we see it in some places in Western Europe. I'm sure it's happening in other places as well, where there's much more attention now on getting everybody to have basic literacy in computation. Okay, we banter around phrases like computational thinking, whatever that means. And the goal is to figure out if once you got two big areas, people always want to put them together. Right? That's how you do hot topic research. That's how you solve important problems. And there's a couple of different ways this cloud collision can work out. One is to build learning tools, right? Which is the kind of thing that many people in this community do. You make enhanced IDEs, better debuggers, style checkers, feedback systems. You think about personalized learning. With the right kind of data, you really can help people understand what kinds of mistakes they personally have made and try to tune them. So there's a lot of great things that you could do in this space. There's also a collision to come out in curricular content. Right? There are discussions now, should everybody learn machine learning? Right? If we taught it to everybody, we wouldn't have to worry about 300 students in the machine learning class while nobody's over in network. You'd figure out how to do it properly. People are creating degrees in data science. Right? Because data science is an aspect of machine learning and the big part of this. There was a talk at the Blocks and Beyond workshop on Monday about machine learning APIs in Scratch, which is a drag and drop language for elementary and middle school students. Okay? This stuff is happening. So we have to think about what should happen when these two fields come together. And I think this is something we have to remember. Machine learning is a tool. It can be a useful tool. But the underlying concept that we're trying to get across to students is thinking about data thinking. Right now we're using machine learning. We used to use other techniques. The techniques will continue to evolve. And data thinking is a mindset. It's a way of looking at your problems. It involves a lot of pieces. It involves finding data that's relevant, right? Searching online and deciding this one's good, this one isn't. It's about confronting noise and errors in your data. It's about understanding the bias in your data and knowing that it might be there and knowing how to correct for it. It's about organizing your data, creating models, a lot of the kinds of things that we talk about. It's about processing things efficiently so that when you grab a large data set, you actually can do your computation. It's about maintenance over time. Just because I got my script to run now doesn't mean it'll run next month when the new set of data comes out. How am I going to maintain all this? It's about interpretation and so much more. And there's some good writing happening on this idea of how you have to think about data. If you haven't seen Hadley Wickham's Tidy Data article, it's a very nice description of good data practices and organizing data to work effectively in R. Now, maybe you're not working in R, but if you are working in R, he kind of sets up how you think about organizing data to work successfully against the R's APIs effectively. And they're good practices in general, but it definitely has a bit of an R influence to it. And a lot of the R influence has to do with setting things up for functional programming, because you're doing a lot of combinators over data, a lot of built-in operations for working with your data. The point is, if you look at this list and you think about computer science, you think about data science, elements of both of them are in these items. Right? You're not going to work with only one of them. And I think if you bring together data science and data structures, what you're really getting at is we need to be thinking about computing as data-centric. Thinking about the different flavors of data that we have to work with to work and program and build infrastructure in the modern world. And data-centric, it's mixing early concepts from both computer science and data science. What do I mean by this? Here's one example of what data-centric computing could look like. First of all, the idea is to think about turning questions about data into programs. Right? We're not just turning them into spreadsheets and then kicking them off to Excel. There's actually programs under there that we want to think about. How do we break down those computations? How do we think about it? Remember that decomposition into solution structures we talked about for Rainfall? It's what's going on here as well. We have to be able to take problems, decompose them into questions that will realize some of them in programs. So what if you started with data organized in tables, which is something most students have seen before, in some fashion. And before you teach them any loops and the conventional things that we talk about in Intro CS, you teach them how to sort, select, compute stats over tables. You're getting them practice in libraries, in composition, in thinking about decomposing problems into ways that you can build up solutions. You can think about interpretation and bias and errors and a lot of these issues. We have to teach them to create small test data. A student comes in and says, okay, I'm going to do this analysis on baseball statistics or whatnot, and I grabbed this great data set off the internet and it's got 5,000 lines in it, and here's what my program said. Is your program right? That's what my program said. There's a discipline to this. We know this discipline. Right? In this community, we know how to think about testing. We have to teach students how to test in the context of data and data analytics, which isn't something we usually think of, but it's something that really comes from the computer science side of this. Once they have these tools, they can sanity check data. They can do some automatic detection of errors. They can do the conventional techniques from data science of visualizing data, looking at distributions, right? Sanity checking is something that draws on both fields. At some point, you outgrow tables. Right? And when you outgrow tables, now you can look at how do we outgrow tables in computer science? Well, we organize things in trees or graphs or hash tables. We also outgrow tables in a data science perspective. Instead of writing manual data structures and algorithms, well, now we're training models and having models help us figure out how to do our program computations for us. So this is a sense of what it might mean to meld computer science and early data science into a data-centric view of computing. This is something else that we are working on quite a bit. At the K-12 level, we bundle those first three, into a curriculum called Bootstrap Data Science. Bootstrap is a national scale with some international outreach series of curricular modules for K-12 that you can embed into other courses. And so we can embed this into a stats class or a business class or a science class or math class or social studies class. So if anybody's trying to think about some of these issues in K-12, feel free to come up and talk to me. We've been doing this for 20 years with K-12. Bootstrap's been around for 10. We got a lot of expertise of working with schools and integrating computer science into things they're already learning. At the collegiate level, well, you can take this whole thing and think of this as your intro collegiate course. And this is something we are doing at Brown. We've got a new course running this semester that I'm teaching. That's called, we call it Computing Foundations Data, but it's really data-centric computing. And the takeaway I want you to get from this, don't let CS and data science diverge too early. We're seeing it happen. We're seeing places create the Intro to Data Science class, which is different from the Intro to Computer Science class. And there's a lot of common foundations in thinking about data and testing and correctness and structure that both of those need. And a downside to letting them diverge too early, first of all, students might not see the connections. Second, a lot of our students don't actually know what they want to study. And by doing them together, you give students the chance to try out both flavors of work and then see what interests them more going forward. This is, I think, one of my bigger policy considerations, especially at the collegiate level right now, is seeing these things diverge too fast, and it'll be hard to pull it all back. All right, so let's wrap up with some takeaways. I gave you some points throughout the talk that I think are worth us remembering. The things that we take for granted are not obvious for the students. Transfer's hard, and you can't just replace misconceptions. Working on these needs little code. It needs talk alouds. It needs interaction to figure out where students are at. It's all key to getting started and making headway there. Now, it's still good to leverage big code and big data. I'm not saying there's no place for this. There is a place. It's going to help us tune what we're doing. But we have to, again, remember that we are trying to tune students' understanding. We are not trying to tune products in an educational space. So we have to keep the big data and the little data, the big code and the little code, all in balance. They ask different questions. A lot of what we've seen in our own work, we start with one, we go back into little code to dig deeper. We try to build tools to automate what we're finding. We get more results. We go back into little code. It's a very cyclic process that we find. You don't want to discount it. And you do need both because they ask different questions. The fact that both matter should seem semi-obvious. I mean, ask anybody who does HCI. They do talk alouds all the time. So why do I think this needs to be said? Because I keep getting review comments like the following. This study has only got data from 12 students, so it's pretty weak. It would be more compelling with more data and quantitative results. Not if it's a question that has to be answered qualitatively. When I stop getting this comment about studies that needed to be done qualitatively, I'll believe that it's obvious. Right? So there's my other plea to you. Please don't write this. Right? If the person did not do a study that was amenable to quantitative reasoning, don't ask them for quantitative reasoning. It annoys us. Okay. Respect, there's likely a lot you don't know about education. I imagine many of you still think that learning programming improves math skills. That would be another talk for another day. But I'll stop here. I'll take questions, and thanks very much again for staying through the conference today.
I thought your approach to having students talking while they were programming was very, very interesting. But I took a different lesson away from it, and that is that maybe we should be using that kind of study to help people doing programming language design, because it seemed quite clear that languages that disallow aliasing or might disallow hiding would eliminate this whole class of confusions. And there may be other lessons like that that you could imagine taking in terms of programming language design.
Right, and I'll cite here Andy Stefik and Stefan Hannenberg have done a lot of work promoting the idea that we need more user study and HCI focus in language design. There was a talk earlier today from Brad Myers, Jonathan Aldrich, and a couple of other folks looking at these issues. This is something that comes up, and I do think language design has to be part of it. One of the challenges I see, though, is when somebody's doing a talk aloud, they have a very narrow focus. Right? They're looking at that particular problem. And what you don't necessarily see is the forest. So we can do a talk aloud and we'll get insight on what people are misunderstanding at a local level. But for a language to work, all the pieces have to work together. And I think that's where some of the tension comes up in that, is you need a certain degree of expertise to make all those pieces play together nicely. But I do agree we need more of that to get to good language designs.
Hello. I really loved your misconceptions about misconceptions slide. And the thing I'm left wondering is, I think most people in this room could not write the wrong answers you presented. So do the misconceptions ever get eliminated? What happens?
Well, so you can train students out of misconceptions. They just have to see it several times, and it's not you talking. Right? They have to actively retrieve the thing that they were misunderstanding and rework it properly. So misconceptions can go away. There's a fair bit of literature in education psychology about how that happens. It just takes more instruction and more direct work than I think most of us who've never done that before would recognize. And in terms of coming up with initial misconceptions, initial ones you get from seeing what kinds of questions students come into office hours with. The rest of them you get by just having them talk and them saying something really strange and probing on it and saying, what do you mean, what are you thinking? And then you find out that they've made connections between two things that you didn't even think had anything to do with each other, but they saw them in the context of the same homework problem, so they associated they must matter. So you can make headway, but you have to listen carefully. And if you ask students, they'll tell you a whole bunch. It's sobering.
Hi, thanks for an amazing talk. I have a question and a comment about the research on analysis of references in Java. So I guess the comment is, it's really a difficult question, because to answer this in Java, you really need to understand that there are objects, there are references, you need to know how they are copied. And I'm scared to say this, but probably it would be easier to ask this question in like C or C++ when you have these explicit pointers, because students would then probably see more explicitly what's happening. So the question is, do you know if they had background in compiler systems by the time you had this study, and if you saw any correlation?
So I'm pretty sure that there was fairly little coursework in compilers for most students. Like a couple of them might have taken it along the way. So they wouldn't have had a lot of that. Whether they had C++ or not really would have depended on which courses they had taken. I think many of them would have had some of that experience. And while I think it's probably right that the misconceptions would manifest differently, pointers would bring in different dimensions than non-pointers. What we were looking at is they're going out to program in these languages. They're going to make these mistakes in whatever language they're told to work in. So we kind of have to understand them where they are. But I agree it could be interesting to see whether pointers would have made a difference there. But that wasn't something we asked them when we did the kind of demographic surveys to see what they'd had coming in.
Hi, Kathy. This was a really great talk. One thing I was thinking about kind of throughout the talk was kind of what's at stake. Like, say for these students, third, fourth year students with these misconceptions, like, do they figure things out by the time they graduate? Do they figure it out a few years into industry? Or are they failing coding interviews? Are they dropping out of the entire program? Kind of, what happens if they don't figure this stuff out?
I wish I knew, and some of you who are in industry can tell us. No, I mean, seriously, what kinds of errors do we see people making? And it may be that some of these issues are things that students, they just never write code that runs into this. We don't know. It's a good dimension that it would be nice to know, but it requires some kind of longitudinal study with people who get them on the receiving end. And that's just not something we've been in a position to do. I mean, many of the students in these courses were seniors, so they were on their way out. And I think part of it is we spend a lot of time teaching them programming carefully in the beginning, and then we just kind of figure they're going to pick it up by osmosis. And what the conceptions literature says is, yeah, they're picking up all kinds of things, but they're not necessarily picking them up in a clean way. They're not being taught it, they're not being challenged, and that was one of the reasons we wanted to do the study. Like, what had they picked up about all this stuff over time? Again, it's sobering.
Hi, I have a question about self-proclaimed Java experts. So it's possible, for example, in Google they have C++ guidelines that don't allow them to use exceptions. Throw exceptions, you can't use that. So people could be C++ experts in the subset that they tend to use and not be like general, complete C++ experts. Like they might miss a lot of details, but still.
Context is everything in this kind of work, and it's one of the things that makes it hard. So yes, I agree. You might struggle on this one thing, but maybe you never use that because it's outside of the practices of your organization. This is why I think getting more of this work out of the university level would be very interesting to do. It's not something we're in the position to do. We did think we were focusing on fairly standard things, though, like references seemed pretty innocuous. But I don't know how much they actually use it when they get into jobs. I don't know.
Something as someone in the industry who I've seen that people don't understand is the evolution of software and how the way you write the software today will affect how what it becomes 5 years or 10 years, or the modular aspect of software, programming the large versus in the small. I loved what you did on programming in the small, maybe. So can this be adapted to teaching how to program in the large?
Probably. I mean, anytime we're teaching, right, we're teaching a set of skills, and if we were teaching programming in the large, we would teach them a different set of skills than in programming in the small. I think even in the large, there would be good use for talking to people about what decisions they were making, what did they see, what evolutions did they anticipate. I don't foresee us getting that data rapidly from looking at kind of the big code repositories. That said, I personally don't do programming in the large, so I would not be the one to teach this. But again, people who think about software in these other domains, this is a good chance to start asking these questions, bring people on board who know some of this user study literature. Either HCI folks know it, computing ed people know it, and trying to ask some of the questions. They're all good questions.
So, first of all, I'm not an education expert, so if any term I use happens to overlap with some education term,
got it.
Ignore it. And I'm curious, like in your study with the Rainfall program, so programming has lots of parts, obviously, and two big parts are, I guess, what we call problem deconstruction and solution construction. A lot of what you described were sort of constraints on how people came about the solution construction. What kind of things did you see on the problem deconstruction side, out of curiosity, or was that sort of addressed already?
No, and that was one of the things we were very much looking at, was the interplay between how they talked about breaking down the problem and how they talked about putting the code back together again. You will see some students are thinking in terms of what I call tasks, right? The high level, what are the things that have to go on here? And they will articulate, okay, I'm going to have to get this thing to happen. I think this piece of code does it. I'm going to get this thing to happen. I think this piece of code. They're thinking a little more semantically about the tasks. In contrast, you have students who they say the words, like they say, I have to sum up. So they sound like they're talking like a task, but when they get to the code, they're simply talking about the syntax of writing a loop that does a sum. And you can tell that they haven't really thought about the interaction of the different parts of it. So they can see the pieces often, but they don't think semantically enough to pull them together. So I think there is a big difference of that point at which you start thinking semantically, you seem to get a lot better at this. And that's kind of consistent with what the ed literature says also, but it is something we see in the talk labs. Yep.
So I was wondering if some of this actually goes back to an old controversy, whether you can actually teach these programming languages without exposing the students to the lower level technical details of the machine. And if you can comment on that particular controversy, that is still really not, right? There's lots of different institutions that do it differently.
Yes, there are many, many different ways to go about the teaching of this. Students need some kind of model of how the machine is working. That does not mean that they need the registers, the bits, right? I mean, you have to decide what level of abstraction you're going to talk about. So for example, you can talk, if you're in a language without side effects, you can teach them a model of program evaluation that's just based on substitution for function calls. And that model is fairly easy for them to manually execute, but it misses some of the nuances that they're going to run into when you do start getting into programs with state and whatnot. So I think what the conventional wisdom in computing education is around is, yes, students need a model of evaluation. We use the term notional machine for that, but it's basically semantics, right? But there are different semantics you can give to a language. And I think one of the big understudied problems in this space is semantics usability from a learning perspective, right? We've got all kinds of great mathematical properties of semantics, but the usability, the cognitive overloads, that's a wide open question, and something that we have one of our PhD students starting to look at that. We're running studies where we give them different semantics and have them do different activities and see what works and what doesn't. So I think there's wide agreement that it's an issue. We don't have answers yet, but we'll come back when we got them and let you know what we found.
Hi. Great talk. You focused on going from big code to like machine automation, but today we use teaching assistants in our classes, and I'm wondering how you feel teaching assistants fit into this picture.
Teaching assistants can be interesting because, and it kind of goes back to the semantics question a little bit, right? I may have a conception in my mind of what I want my students to be thinking about right now, and my teaching assistants go off and talk about something completely different. Like I've had students come in and say, well, I'm worried about the efficiency of this. I haven't said the E word. Where'd you get the E word? Oh, the TAs. Okay, no. So I think there is an issue there that we're all trying to convey models of how programs work to students, and we and the TAs might not be consistent, and yeah, I think that is a challenge. And I think the TAs often have some of the same misconceptions the students do. They're just, a little bit ahead of them. So I don't have a solution to that problem other than being aware of it. But yeah, I agree, it's definitely an issue of how you keep a course staff in sync. And that is a place where tooling could help, because at least then there's kind of a definitive reference. You don't have to go to the professor's office hours to ask it. But then again, what are the right tools? How do you design them? We've got lots of research to do. It's great.
I will ask one last question. You and I have pushed explicit program teaching over implicit by osmosis teaching.
Mm-hmm.
Do you think you can see differences in your work, especially in the first part?
You mean for whether students have learned by example or whether they're learning by a process?
Instruction, how to construct a program.
What I think I see happening is when students have been given an explicit way to construct a program, what it's doing is it's teaching them a skeleton of a solution that they can retrieve very quickly. And there's real value to that. There's been research looking at how people approach problems. Do they start from this little tiny grain and try to build up, kind of bottom up? Do they grab something bigger picture and try to fill it in? So I think these explicit instruction techniques give them these mechanisms, these templates, these schemas. They go by different terms depending on which papers you read. It gives them something to copy and latch onto. So it does get them over an initial hump, as long as what they grab is relevant to the problem. But I think, what happens with a lot of the example-driven stuff is they learn a little bit from this example, a little bit of that example, and now there's all kinds of colored dots on the picture, and some combination of them are going to get retrieved and smashed together, and it gets interesting. I think we've seen that, those of us who teach, and yeah, so we're still balancing it.
Let's thank Kathy again for that.